Alrighty, so today we're going to be working with number 61. That's going to be coming from chapter 19 of the Matter and Interactions textbook. I'm going to post the question below so you can look at that. So this is going to be the figure that we're going to be looking at. And so that's going to be a big part of this equation, a big part of this problem, so make sure you know that and you save that. So first, we are asked, show the electric field inside the slab at X, of the two locations marked with X. And so we know that it's going to be decreasing with X, because at the left end of the iron slab is connected to the negative terminal of the voltmeter, and the left terminal of the iron slab is connected to the positive terminal. Positive terminal of the voltmeter, so that we know that the electric field direction is left side to the right side of the iron slab, and so we know that it is going to be increasing with X. And so in part B, we are asked to explain why the magnitude of the electric field is different at these two locations. And so we know that the mobility is going to increase with X, because the different temperatures and all that has a factor with that, and it's also going to be increasing with E. And then for part C, we're going to get I is equal to En AUE, where N is the number of atoms per cubic meter, A is the area, U is the mobility of the electrons, and E is the electric field. And so we know that, and so we know that there's a high mobility of the irons to the right side, so we know from the equation here, the electric field must be smaller to the right. And so that's how you get that one. And then for part C, we are going to for part C, we're asked to, at a distance X from the left voltmeter connection, what is the magnitude of the electric field in terms of X and the given quantities. And it tells us just what we're allowed to use and what we're not allowed to use. And that's going to be for part C. So we're going to be here. And so we know that I is equal to En AUE. As I said earlier, A is going to be length time width because that's the area. U is equal to U sub naught plus kx. And that was given to us in the problem. So we just use this equation, we plug in, and we're going to solve for E. And that's pretty much all you do there. And for part D, we know that the positive lead of the voltmeter is connected to the lower potential end of the slab, and so it's going to be negative, because as I said in previous videos and also now, potential decreases as the electric field decreases. And so that is how we get that, and we know that it's going to be negative. And so for part E, which is pretty fun, we get to do some integration. That's always my favorite part. And so we're going to need to find delta V. And so we know that delta V is equal to the integration from 0 to D, because that is what our figure says, that the whole length of it is D. So that's how we get our limits of integration there. And we know that E, as we found up here, is going to be equal to this, and dx. And so we know that I over ENLW is a constant because it doesn't have x included, so we're just left with 1 over U sub naught plus kx dx. And we're just going to solve that, take the integration of that, which is going to be the ln of U sub naught plus kd minus ln of U sub naught. And that's going to be the simplification of that. We know that according to the natural log rules, we can divide those, same thing as subtracting, so that's what I did here, just simplified that. And for F, we are asked to find the resistance. And so we know that I is equal to delta V over R, and R is equal to delta V over I. It's just kind of changing up that equation. We know what delta V is, and we know what I is. We found delta V here. I mean, you can just solve that for I. Or I just kind of left I there. because it is going to be a constant and it will cancel. And you just simplify that, and that's what you get there, and that's going to be the resistance.